In this new video in our series on doing things with geometric algebra, we're going to see how to use geometric algebra to solve what was described as a hard contest problem, which comes from the channel Mind Your Decisions, which I encourage you to check out because they have a lot of very interesting problems of many types. Now, I'm not going to claim that geometric algebra is necessarily better for solving a lot of these contest problems than the methods that are shown in the videos such as Mind Your Decisions, but it's something that might be considered. So, our adaptation of the problem that appeared in Mind Your Decisions is going to use an arbitrary value of k here and an arbitrary angle instead of the specific values that are given by Mind Your Decisions. A PDF of this solution is linked in the video description. And what we will do in this video is first we will go through the ideas that we're going to use in the solution. Then we'll formulate a solution strategy and present the geometric algebra formulation of the problem. Then go ahead and actually solve the problem, and I hope you'll stick around to see the verification of our solution via an interactive geometric or GeoGebra construction, which I really encourage you to try out. So the ideas that we will use in this video, first of all, for any two vectors u and v, their outer product, the wedge product, is equal to the bivector part of their geometric product. The vectors v exponential I theta and v exponential negative of I theta are rotations of the same vector v by the same angle but in opposite directions, as you can see here, if we define this as the rotation direction of the bivector and the unit bivector, pardon. There are a few other little things here that are not terribly important, but if we know them, they move the solution along a little bit more rapidly. If we reverse the vector and the exponential, as we do here, we reverse the sign of the exponential. And knowing this, we can arrive quickly at, among other things, if we have a unit vector multiplying an exponential on both sides, that evaluates just to the exponential of the negative of that angle here. So our solution strategy will be to use rotations of vectors and the outer product to determine L. Remember, what we were given are the angles, or is the angle alpha, the distance d, and k. We are not given L. So we're going to use this method to find L, and then knowing L and KL and this angle here, we can find BC from law of cosines. Our GA formulation, here is the sense of our unit bivector for the plane. We will define this as our direction of the unit vector d, and then this unit vector is just that same d hat times the exponential of negative I alpha, because we're going in the sense contrary to the sense of the unit bivector. And c here, the direction, or this direction, is d hat times exponential of positive I alpha, because we're rotating in the same sense as the unit bivector. So b here is just kl times this unit vector, and c is just l times that unit vector. What we'll do then is notice that c minus d is parallel to d minus b. And because c minus d is parallel to d minus b, their outer product is 0. And remember that the outer product of any two vectors is the bivector part of their geometric product. So now we'll just beat on this thing a while and do algebra. First we'll expand C and D as I described in the previous slide. Expand these, and then we'll note a few things here. Here we have an exponential bracketed on both sides by a unit vector. So as you saw earlier, that will evaluate to the exponential, the negative of that I alpha. Also, the bivector part of a sum and difference of different terms is equal to the bivector parts or the bivector parts of each, or the sum and difference rather, pardon, of the bivector parts of each term. And so we notice here that d squared is a scalar, so its bivector part is 0, so that will drop out. And when we use these ideas to simplify this, we come up with this expression. So we'll work on that in the next page here. If we factor out the L here, we end up with this bivector part expression. And then we notice that the bivector part of e to the minus I alpha is negative I sine alpha, negative of I sine 2 alpha, and negative of I alpha again. So when we simplify all this, we come up with L, which is what we needed to find in order to use the law of cosines. L is k plus 1 times d sine alpha over k sine alpha. Now, because sine 2 alpha is 2 sine alpha cosine alpha, well, you can read this here, L becomes just this. And now, from the law of cosines, BC here, you can read this yourself again. We do a little algebra here and make some substitutions, and we come up with this expression, which we'll work on a little bit more. We're repeating what we saw in the previous slide. Then we use the trig identity that for any angle theta rather, cosine of 1/2 theta is the square root of 1 plus cosine theta over 2. So making that substitution here, when the smoke clears, we come up with BC is equal to, well, you can read it here, this was L. So let's see how we did on this. That was our result here. And in this geometric or GeoGebra construction, we can vary the distance d, we can vary the angle alpha, and also the factor k. And in GeoGebra, we can actually do all these calculations and also compare them to the true lengths. So the true value of L here is 11.32, and as calculated, it is also 11.32. The true length, BC, is 29.6, and the calculated version is also 29.6. So just to show that we weren't only lucky in choosing the right values here, we'll see if that solution holds up as we vary the angles. And as we value k, or vary rather, and as we vary d. So GeoGebra is a free program, and it's very valuable for checking solutions like this. So back to our presentation here. Again, a PDF of the solution is linked in the description. And I hope that you will consider joining our pre-university geometric algebra group in LinkedIn. And I'll put the link in the video description. So I appreciate your attention here. I look forward to any corrections and comments. And thank you for your time.